In this class, the lecture is on semiconductor materials and properties. The objective of this class is to be able to understand the properties of semiconductor materials, which includes the two types of charge carriers. We are going to be looking at the two types of charge carriers, which are electrons and holes that exist in a semiconductor, and the two mechanisms that generate currents in a semiconductor, which are due to drift and diffusion. So at the end of this class, you should be able to understand and explain the two types of charge carriers and the two mechanisms that generate currents in a semiconductor. So we're going to start with semiconductor materials. So the major semiconductor material that is being used in electronic circuits is the silicon. So the silicon is by far the most popular and the most common. There are other types of semiconductor materials like gallium arsenide and gallium phosphide, but the most common is the silicon, and is the silicon semiconductor material we are going to be discussing for this class. So we'll start with the intrinsic semiconductor. So in explaining the intrinsic semiconductor, we look at the structure of an atom. So an atom is composed of a nucleus. So the nucleus is at the center, and which has positively charged protons and neutral neutrons and negative charged electrons that orbit around the nucleus. So the innermost shell has two electrons, two charged electrons. The second shell has eight, and the next one has 8 electrons. So depending on the type of the atom in the periodic table, we'll know the number of electrons that exist in the outermost shell of the atom. So the electrons that exist in the outermost shell is called the valence electron, and they vary depending on the type of atom. So for silicon atom, 4 electrons exist in the outermost shell, and since 4 electrons exist in the outermost shell, they are called group 4 atoms. For some atoms that 3 electrons exist in their outermost shell, they are called group 3 atoms. So group 3 atoms are boron, aluminium, gallium, and indium. Then for atoms that 5 electrons exist in their outermost shell, they are called group 5 atoms. As we can see from the portion of the periodic table, examples are phosphorus, arsenic, and antimony. So we can see the structure of a silicon atom. So this figure shows 5 non-interacting silicon atom, and as we've said before, 4 electrons, they have 4 valence electrons. Then when this silicon atom come in close contact with each other, the valence electrons, they interact to form a crystal, and the final structure is a tetrahedral configuration in which the silicon atom has 4 nearest neighbors. So you have the silicon atom that has 4 silicon nearest neighbors. The valence electrons are shared between the atom, which results in what we call covalent bonding. So covalent bond results when valence electrons are shared between the atom. So this is the tetrahedral configuration that we can find here. So the 2D representation of the silicon crystal is found here. So when the temperature is at 0 degrees Kelvin, each line between the atom represents the valence electron. So at 0 at 0 Kelvin, the electron is in its lowest possible energy state. So we call that state the valence band. So the electron is in its valence band, and we can say that it's covalent bonding that is present at the moment, because the valence electrons are shared between the atom, are shared between the silicon atom. If a small electric field is applied to the silicon atom in this structure, the electrons will not move because they are still bound within to their individual atom. So at 0 Kelvin, the silicon is an insulator, because when an electric field is applied, no electron is moving and covalent bonding is at work. So at 0 Kelvin, the silicon is an insulator because no charge flows even when an electric field is applied. And we said that at 0 Kelvin, the atom is in its lowest possible energy state. So at 0 Kelvin, the valence electrons occupy the valence energy band. So it's at the lowest possible energy state. And if the temperature is increased, so we've seen at 0 Kelvin, but if the temperature is increased, the valence electrons, they will gain some thermal energy, and the thermal energy that is being gained may be sufficient to break the covalent bond. So the valence electron will move from its original position. So looking at this figure, the valence electron, it was formerly here, but with an increase in temperature, the valence electron will gain some thermal energy that will cause the covalent bond to be broken, and it will move away from its original position to this position. And in order to break the covalent bond, it needs to overcome a certain minimum amount of energy called the band gap energy. So previously, when the silicon atom is at 0 Kelvin, it is in the lowest possible state, which is the valence energy band. So at the point at which it breaks its covalent bond, it moves into the conduction band. And the difference between the conduction and the valence band is the band gap energy. So the electrons that gain the minimum energy, they now exist in the conduction band, and they are free electrons. So the free electrons in the conduction band can move within the crystal structure of the silicon. And when they move, when electrons move, when the charges, when they move, current is generated. So we can see the diagram of the energy band that has been discussed previously. So I talked about the valence band. So at 0 Kelvin, the silicon atom, they experience covalent bond. So that's the sharing of valence electron. And even if an electric field is applied, there's not going to be any movement. But for an intrinsic semiconductor, when the temperature is increased, the electrons, the atom within the silicon structure, it gains some thermal energy. So the valence electron, they break away from the covalent band and they gain this band gap energy called Eg, and they move to the conduction band. So when the valence electrons, when they move within the conduction band, it's the movement of the electrons creates current. So there is no energy band, no electron can exist within this forbidden band gap. So that's why we call it forbidden band gap. So it's called the band gap energy. And the band gap energy is the difference between the valence band and the and the conduction band. So that's the difference between these two energies. No electron can exist within the forbidden band. Then we can, based on this conduction, valence, and forbidden energy band gap, we can classify different kind of materials. So the materials that have large band gap energies, definitely they are insulators, because there is a significant amount of energy required for them to move from non-conducting, which is the valence, to the conducting band. So materials within the range of 3 to 6 electron volts, they are insulators. Then materials that have a band gap energy in the order of 1 electron volts, they are semiconductors. Then conductors would have even much more lower band gap energy compared to semiconductors. So the net charge in a semiconductor material is 0. We've discussed that when the electrons, they gain certain amount of thermal energy, they break, the covalent bond is broken, and they move to another location within the crystal. And given that the net charge in a semiconductor is 0, it means that the semiconductor is electrically neutral. So when a negatively charged electron breaks its covalent bonds and moves to another position different from its original position, an empty state is created at that position. And as the temperature increases, more covalent bonds are broken and more free electrons move to another position, and even more empty states are created. And that empty state is a positive empty state, given that the net charge in the semiconductor is 0. So a valence electron that has a certain thermal energy and is adjacent to an empty state, that valence electron can move to that empty state, making it appear as if a positive charge is moving through the semiconductor, because that empty state is essentially as a positive charge. So that positive charge is called a hole. And in semiconductors, we have two types of charged particles, charge carriers, that contribute to the current. We have the negatively charged electrons and the positively charged hole. So remember that the objective of this class is to be able to understand the two different types of charge carriers that we have, that exist in a semiconductor. So for an intrinsic semiconductor, these are how these two charge carriers are created. Then the concentration of electrons and holes, they are important parameters in determining the characteristics of semiconductor, because we want to know the concentration of electrons and holes that are moving within the semiconductor material, because that will determine the current, and that will determine the conductivity of the semiconductor material. And the number or the concentration of electrons and holes, they influence the magnitude of the current. So in an intrinsic semiconductor material, the densities of electrons and holes are equal. So equal number of electrons and equal number of holes are created. as we have already seen here, because the net charge of a silicon material is the net charge is 0. So when an electron moves to another position, an empty state, which is a hole, is created at that position. So this means that in an intrinsic semiconductor, the densities of electrons and holes are the same thing. So since it's as a result of thermal increase in its energy, so we have the notation called Ni, which is called the intrinsic carrier concentration for the concentration of free electrons and holes in a semiconductor as a result of if the semiconductor is intrinsic, and the formula is given by the highlighted equation. B is a coefficient that is specific to a semiconductor material, and the unit is in centimeter per unit per cube centimeter, then Kelvin minus 3/2, that's the unit. Then T is temperature in Kelvin. In this case, E is an exponential, so exponential Eg. We've seen this term before. Eg is the band gap energy, and these are the specific band gap energy for different semiconductor material. K in this case is a Boltzmann's constant, and it's specifically given by this number. Then T is the temperature. So this formula is the equation that tells us the number of electrons and holes that can be generated in an intrinsic semiconductor for a particular temperature. So in intrinsic semiconductors, it is an increase in thermal energy that produces carriers and consequently holes. We want to calculate the intrinsic carrier concentration for silicon at this temperature. So we just apply the formula. We'll get the value of B from this table, then the temperature we're given, and the band gap energy we are given in this table, and the Boltzmann's constant, it's specific, then the temperature we are also given. So we calculate the intrinsic carrier concentration of holes and electrons. We calculated it as 1.5 times 10 times 10 raised to power 10 per cubic centimeter. So this number, it may look large, but the concentration of silicon atom is 5 times 10 raised to power 22 per cubic centimeter. So when you compare this number with this number, we can see that the number of intrinsic carriers, either holes or electron, is very small compared with the concentration of silicon atom. So the intrinsic carrier concentration as a result of thermal energy, when the temperature is increased, the number of holes and electrons we can get is not very good in the case of the intrinsic case. So remember that it is these electrons that actually create current. So that means that if we just want to sit on the intrinsic semiconductor, if you just want to sit with it and just use it, we're not going to be able to generate much current, because the number of electrons and holes that are being produced are not is not impressive. So that will lead us to another kind of way of generating more electrons and holes, and in that case we look at the extrinsic semiconductor. So it turns out that this number of carriers, they can be increased by adding some controlled amount of certain impurities. Impurities in this case means either we add a group 3 atom or a group 5 atom. Remember, the silicon is a group 4 atom. So we need to add a controlled amount of this impurity, and as we'll be seeing later, this process is called doping. Because when a desirable impurity, not just any impurity, like I said, when it enters into the crystal lattice, it would replace or substitute the silicon atom, and in the process is either going to give us holes or electrons. So we'll look at the first way of generating more electrons, because we don't want to be stuck with the intrinsic case where we have to increase the thermal energy. So when a group 5 element is added as an impurity into the silicon lattice, so a group 5 element in this case can either be phosphorus or arsenic. So when it is added into the silicon lattice, the phosphorus would replace one of the silicon atom. So remember that the phosphorus is a group 5 element, and we just need 8 valence electrons to complete the orbit. So there is one extra remaining, because 4 out of the 5 of the phosphorus valence electron will satisfy the complete orbit. So one extra is going to be left hanging, which is the 5th one. So that 5th one is loosely bound to the phosphorus atom. So at room temperature, we don't even need to increase the temperature for extrinsic semiconductor. At room temperature, the electron already has enough energy to break the bond, because it's already loosely bound. The covalent bond is very loose, because the 8 valence electron has already been completed. So this 5th one is loosely bound and is even free to move within this crystal lattice. So, and it contributes to electron current in the semiconductor. And when this 5th electron, when it moves to the conduction band, a positive charge ion is created on the phosphorus. So the phosphorus becomes positively charged. So remember that the net charge in a semiconductor is 0. So when this 5th electron, when it moves to the conduction band, a positive charge is created on that phosphorus atom. So this phosphorus atom is called a donor impurity, because it donates an electron that is free to move and that contributes to current. So when this free electron, when it moves, a current is created. So the remaining phosphorus atom, like I said, has a net positively charged. The atom is immobile and it cannot contribute to the current. So it's the electron that contributes to the current. So when a donor impurity is added to a semiconductor, free electrons are created. So no holes are created. So it is electrons that are created, and the process is called doping, and it allows us to control the concentration of free electrons in a semiconductor, because we know the controlled amount of phosphorus we are adding into the semiconductor. So a semiconductor that contains donor impurity atom is called an N-type semiconductor, given the fact that negatively charged electrons, they move within the crystal lattice. No holes are produced. when a donor impurity or when a silicon atom is doped with a donor impurity. No electrons are produced. No holes are produced. The positive charge that exists on the phosphorus atom, that one is immobile, doesn't move. It is the free electrons that move, and the electrons are negatively charged. So the type of semiconductor that is produced as a result of donor impurity are n-type semiconductor, and because of negatively charged free electrons are produced. So we are still on the intrinsic case. So we now look at the case whereby we can produce holes that will contribute to the current. So when a group 3 element is added into the silicon lattice, boron is a group 3 element, and remember that we need the four remember we need 8 electrons to complete the outermost shell. So the boron has only 3, is a group 3 element, so it only has 3 valence electron. So that means there's an extra empty bond. So it leaves one bond that is open. So we can say that that extra bond, that extra one that is left to complete the 8 um the 8th electron, we can say that that is a hole. And at room temperature, you don't even need thermal energy. You don't need an increase in thermal energy. At room temperature, adjacent valence electrons, they may gain sufficient energy and move into that open position, thereby creating a hole. So the effect is shown here. So the boron atom itself has a net negative charge. Why does it have a net negative charge? Because of the hole the hole is a positive charge and it has already moved, because an extra valence electron has come into that empty state. So it has, and remember I kept saying that the net charge on a semiconductor is 0. So when a positive charge moves to another position, there will be a net negative charge on the boron atom, and this negative charge cannot move. It is the holes that are moving and they contribute to. So when these carriers, when they move, a current is created. So because the boron atom has accepted a valence electron, it's called an acceptor impurity, and it leads to the creation of holes. So no electrons are created, and this process is called, similarly to the donor impurity, it's called doping too. And we can use it to control the concentration of holes that exist in a semiconductor. And a semiconductor that has a group 3, that has it doped with a group 3 element, is called a p-type semiconductor. So P stands for the positively charged holes that are created. So the materials that are created using impurity atoms is not like impurity, like dirty. It's what it just means is that another atom which is different from the original one has been added into it. So we are talking about silicon material, silicon atom in this case. So when you either add phosphorus or boron, we say we have added an impurity, and we call these types of semiconductors that impurities have been added, we call them extrinsic semiconductor or doped semiconductors. So doping allows us to control the concentration of either negatively charged holes, negatively charged electrons, or positively charged holes that exists in the semiconductor material, and it determines the conductivity and the amount of current that can be produced within the semiconductor material. So the equation that specifies the relationship between the electron and holes concentration in a semiconductor material that is in thermal equilibrium is given by this equation, where N naught is the thermal equilibrium concentration of free electrons, P naught is the thermal equilibrium concentration of holes, and Ni is the intrinsic carrier concentration in the semiconductor material. So at room temperature, each donor atom donates a free electron to the semiconductor. So if the donor concentration is larger compared to the intrinsic carrier concentration, which is the case if it's doped, because as we've seen in that first example, the intrinsic carrier concentration is very low. So if the donor concentration is large compared to the intrinsic carrier concentration, we can just replace the thermal equilibrium concentration of free electrons. We can just replace it as the donor carrier concentration. So therefore, the hole concentration will just, in place of N naught, we replace it with the donor carrier concentration in this formula, and we get the hole concentration as this equation. So similarly, at room temperature, each acceptor atom replaces a valence electron, thereby creating a hole. So therefore, if the acceptor concentration is large compared to the intrinsic carrier concentration, we can replace the positively charged holes as with the number of acceptor concentration, and we replace it with this equation. So in place of PO, we replace it with Na. Then we get the electron concentration. So we want to calculate the thermal equilibrium concentration of holes and electrons that exist in a semiconductor material. For the first case, we have a silicon atom that is doped with phosphorus. Remember that phosphorus, it creates electrons, so you have donor atoms. So the donor carrier concentration is given by 10 raised to power 16, and we know that from the first calculation, this is our intrinsic carrier concentration. Given that the donor carrier concentration is far greater than the intrinsic carrier concentration, we replace the electron concentration in thermal equilibrium. We replace it as 10 raised to power 16. So we calculate the hole concentration as 10 raised to power 4. So similarly, in this case, when it's doped with boron with an acceptor atom, so we replace the intrinsic carrier concentration, we replace it with Na, because we are going to replace the hole concentration with Na, because the Na is far greater than the intrinsic carrier concentration. So we'll now calculate the electron concentration using this same equation, and we arrive at 10 raised to power minus 10 raised to power 3. So when we look at this example, we can see that when the semiconductor material, when it's doped with a donor impurity. The the electrons are the majority carrier. So why are the electrons majority carrier? Because this number is far greater than this number. So when a silicon material is doped with donor impurity, electrons are the majority carriers, while the holes are the minority carriers because they are few. Conversely, when a semiconductor material is doped with acceptor impurity or a group 3 impurity, the holes are the majority carriers because we have more of this, while the electrons are the minority carriers because we have less of the electrons. So uh, so it's important to note that the difference in the concentration between electrons and holes is very great by order of magnitude. So this 10 raised to power 16, 10 raised to power 3, this 10 raised to power 16, and 10 raised to power 4. So in an n-type semiconductor doped with donor impurities, the electrons are the majority carriers, and in a p-type semiconductor doped with acceptor impurities, the holes are the majority carriers, while the electrons are the minority carriers. So going back to our objective, remember we want to be able to explain the different mechanisms that create current in a semiconductor. These intrinsic and extrinsic semiconductors we have talked about. We have known how an electron or how a hole is created, but these electrons and holes are called charged carriers or charged particles, and it is only when they move that is when current is created. So once you look at the two mechanisms by which current can be created in a semiconductor, and those two mechanisms are due to drift and diffusion. So those are the two mechanisms. So the charged electrons we've seen previously, which are the charged carriers which we've seen previously, which are the electrons and holes, they are called carriers. And it is when those carriers, when they move, that is when current is generated. In the case of drift diffusion current is generated as a result of electric field. In the case of diffusion, current is generated when these charge carriers they move as a result of difference in concentration gradient. So we start with the first case, drift current density. So in drift current density, as we've said earlier, is as a result of movement of these charge carriers due to electric field. So when an electric field is applied to a semiconductor, either intrinsic or extrinsic, the electric field produces a force that acts on these charge carriers, which are either free electrons or holes. And when the force acts on them and a net velocity is produced, a net drift velocity is produced, because force acting on any particle will produce a velocity and a net movement, and as a result of the movement we can see that current will be created. So the equation that relates the velocity with the electric field is given by this equation. We have nu n, and this nu n is a constant. It's called electron mobility. So in the case of where the charge carrier is an electron, so this is the equation. So you have the negative sign here because the electrons are negatively charged, and this constant is called the electron mobility, and this is its unit. So for low doped silicon, a typical value of the electron mobility is given by this constant. So the negative sign here is because of it indicates that the electron drift velocity is in the opposite direction to the applied electric field. Then calculating the current density from the velocity, we introduce these two constants. What is E? E is the magnitude of the electronic charge, and N is the electron concentration, and this is the drift velocity. V is the drift velocity of the free electron. So as a result of the electron is negatively charged, so the drift current density is given by this equation here. So we'll now consider, so this is the case for the p-n type semiconductor, that's for the free electrons. So we consider the case of the n-type semiconductor doped with acceptor impurities. So consider the case of the p-type semiconductor doped with acceptor impurities, and it has is generating holes which is not generating current. So when an electric field is applied, a force is produced, and that force results in a net drift velocity, and which results in a net movement, and that velocity is given by this equation, where nu p is the O mobility, is a constant, and for low doped silicon is usually in the range of 480 and is given by this unit. So getting the current density from the velocity, we introduce these two constants, where E is the electronic charge, the value of the electronic charge, and P is the O concentration. Then we are able to arrive at the O density. So it's important to note that for an n-type semiconductor, if this is the direction of the electric field, the net drift velocity is in the opposite direction, and it's as a result of the hole, so it's as a result of the electron which is negatively charged. Then the current density is in the same direction as the electric field. For a p-type semiconductor, the electric field, if this is the direction of the electric field, the velocity is in the same direction, and the current density is also in the same direction. So a semiconductor contains both electrons and holes. So the total drift velocity is the summation of that of the electron component and the hole component, and we arrive at the value called sigma. Sigma is the conductivity, and is given by this equation when we extract the electric field from the current density equation. So this is the conductivity of the semiconductor. Then we introduce another constant called rho. Rho is the inverse of the conductivity and is called the resistivity of the semiconductor. And this equation here, J is the drift current density, rho is the resistivity, E is the electric field, and if the electric field is as a result of applying a voltage, this equation is analogous with Ohm's law. So We replace the resistivity with resistor value, we replace the current density with the current value, and we replace the electric field with the voltage. So we can change the conductivity from a strongly N-type to a strongly P-type by simply doping with acceptor impurities. So conversely, we can change the conductivity from a strongly P-type to a strongly N-type by doping with donor impurity. So being able to control the conductivity of a semiconductor by doping enables us to fabricate a variety of electronic devices that is available. So in the next section, we'll be talking about the p-n diode. So as a result of this selective doping that helps us to fabricate even the transistors too. We now want to calculate the total drift density for a given semiconductor. So we have a silicon atom at this temperature is doped with arsenic atom. An arsenic atom is a group 5 impurity. So you have selective doping. So you doped with this number of donor atoms. So we have like this amount of arsenic atom within the silicon lattice. Then we are given the electron mobility constant and the hole mobility constant at this value, and we specified the electric field as this value and want to calculate the drift current density. So in order to do that, we have already gotten the donor carrier concentration that the silicon atom is doped with, and we know that this donor carrier concentration is far greater than the one that will be produced as a result of the intrinsic case. So we just say that the electron concentration is given by the donor concentration that the silicon atom was doped with. We wouldn't care about the electron concentration for the intrinsic case. So as a result of that, we now calculate the hole concentration, because as you dope with electrons, so the electrons are the majority carriers, but you still have some holes as the majority carriers. So we calculate the holes by this same formula and we get this. So the electrons are the majority carriers and the holes are the minority carriers. So it's an N-type semiconductor. So we are given the electron mobility value as this and the hole mobility value as this. So we can calculate the total conductivity, but then the hole concentration is very small compared to the electron concentration. So we are just going to neglect the hole concentration and just use the electron concentration. So E is the value of the electronic charge, N is the number of negatively charged free electrons, so which in this case is the donor concentration. Then multiply it by the electron mobility value. So we don't need to include the hole mobility value there because the electrons are the majority carriers. So we arrive at this conductivity, then we calculate the drift current density by multiplying with the electric field, with the applied electric field, and we get 173 amperes per centimeter squared. So the current density is, the unit is in ampere per centimeter squared. So I've already said this previously. So since the negatively charged electrons are far greater than the positively charged holes, the conductivity is majorly a function of the electron concentration and mobility values, electron mobility values. So um, when you need to mention two factors that are contributing to drift velocity and mobility. So this is the equation for the uh, drift velocity for the n-type case and for the p-type case. So this equation implies that these drift currents, these drift velocities, they are linear functions of the applied electric field. But in practice, this equation is only true where the electric field is small, because when the velocity reaches a maximum value of 10 raised to power minus 10 raised to power 7, any further increase in electric field will not produce an increase in velocity. So it saturates at this velocity. So this phenomenon is called drift velocity saturation. So another thing to note is that the electron mobility values and the hole mobility values, they are functions of the donor and or acceptor impurity concentration. So as the impurity concentration increases, the mobility values will decrease. So it's just a matter of thinking about it, that when you increase the concentration of the electrons or the holes, so when they are more within a specific a fixed area, the mobility values, they wouldn't really, the mobility of these electrons will be limited. So as they increase, they wouldn't really have the chance to move, so the mobility values will decrease. So this as a result of this, it means that the conductivity which is given by this equation is not a linear function of the impurity doping. So it's a linear function of the mobility value, but it's not a linear function of the impurity doping. We now consider the second case where you can generate current in an intrinsic semiconductor, and it's due to diffusion, and it's called diffusion current density. And in this case, the charged particles, they flow from regions of high concentration to regions of low concentration. So this phenomenon is similar to kinetic theory. So as a result of randomized interaction with this lattice atom, half of the charged particles will move from high concentration region and they move toward the lower concentration region. And at the same time, approximately half of the charged particles in the lower concentration region, they will move towards the high concentration region. But there are fewer particles in the lower concentration region than there are in the higher concentration. So as a result of this, the net movement, the net flow of particles is away from the high concentration. So it's from the high concentration to the low concentration. So this is a basic diffusion process in chemistry. So the diffusion of electrons from high concentration to low concentration will produce a flow of electrons in the negative x direction. So we are talking about the electron case. So when the electrons move from high concentration to low concentration, the flow of electrons is going to be in the negative x direction. So given that the electrons are negatively charged, the conventional current direction, so the negative charge is going to cancel out, and the direction of the current diffusion density is going to be in the positive direction, and is given by this equation here, where Jn is the diffusion current density, E is the value of the electronic charge, Dn is a constant, and is the electron diffusion coefficient. The n, the x is the gradient of the electron concentration. So that's in the case of the n-type semiconductor. So in the case of the p-type semiconductor, so the diffusion of holes from high concentration to low concentration, it produces a flow of holes in the negative x direction. So as a result of that, the diffusion current density is also in the negative x direction. Remember, in the electron case, because of the negative charge, the diffusion current density is in the positive x direction. But in the case of the hole, is in the negative x direction. So you have the negative sign. So the diffusion current density for the hole, the diffusion hole density is given by Jp. You have the negative sign. E is the value of the electronic charge. Dp is a constant, so it's the hole diffusion coefficient. The P dx is the gradient of the hole concentration. So note the difference in sign from the n-type semiconductor to the p-type semiconductor. So we are going to do an example to calculate the diffusion current density. So we have silicon at this temperature, and the electron concentration moves from 10 raised to the power 12 to 10 raised to the power 16, from 0 to 3 micrometer, and the diffusion electron coefficient is given by 35. I want to calculate the diffusion electron current density. Diffusion current density. We're going to use this formula. So the value of the electronic charge is a constant. The diffusion electron coefficient given by 35, and the diffusion gradient is given by this calculation, and we arrive at 187 ampere per centimeter squared. So the current density as a result of diffusion is 187, and the current density as a result of drift is 173. We can see that this value that we've obtained is in the order of like 200 amperes per centimeter squared. So it's a very large number, and it's a very large number. And one thing to note is that as I've said earlier, the diffusion and drift current density is a very large number. And meanwhile, in semiconductor materials, maybe the current that we want is in the order of a few milliamperes. So how do we reconcile this? The equation that relates the current with the current density is given by the current density multiplied by the cross-sectional area. So if you want to obtain a current of 1 milliampere, and by calculation you have like 200 ampere per centimeter in terms of the current density, it means that the cross-sectional area that is going to be used is going to be I divided by J, which will result in 5 times 10 raised to the power minus 6 centimeters squared. So this is the reason why the semiconductor materials are really small. So that's why you have semiconductor materials with a size of nanometer size, just because of this phenomenon. And it's important to note that the total current density is a sum of the drift, is a sum of the density as a result of the drift and diffusion components. But fortunately for us, we only need just one component, because it's only one component that dominates at a given time in a given region. So most times you don't need to add the two, the drift and the diffusion components together. And one last thing to note before we close on the drift and diffusion current density is that the O uh, mobility coefficient, the electron, um, the mobility values for the electrons, and the diffusion coefficient values. So these are the mobility values as a result of the drift current density, and these are the current diffusion coefficient values as a result of the diffusion current densities. They are not just independent, but they depend on one another, and they are related. They relate to one another within Einstein's equation. So the dp is the diffusion coefficient of the holes. Up is the hole mobility value. Dn is the diffusion coefficient of electrons. Un is the electron mobility value. So Up is the hole mobility value. Un is the electron mobility values. So they are related with the Einstein's equation, which is approximately equal to 0.026. So we move to the excess carriers. Up to this point, we have assumed that the semiconductor is in thermal equilibrium. So in the discussion of the drift and diffusion currents, we've assumed that the equilibrium is not significantly disturbed. So but in practice, when a voltage is applied to a semiconductor or a current exists in a semiconductor, the semiconductor is not usually fully in equilibrium. So, and why is it so? It is so because when high energy photons are incident on a semiconductor, the valence electrons may gain sufficient energy and break its covalent bond, leading to the production of free electrons and consequently holes. So in the two cases we've talked about, is either when there is an increase in temperature, or there is doping with impurity, either with donor impurities or acceptor impurities. We've not considered the case when high energy photons are incident on the semiconductor. So if high energy photons are incident on the semiconductor, then it will lead to the production of excess holes and excess electrons, even within that intrinsic and extrinsic case. So the excess holes that are produced is given by the N, and the excess holes that are produced is given by the P. If the semiconductor is in steady state equilibrium, then the creation of holes and electrons will not cause the carrier concentration to increase indefinitely, because the free electrons may recombine with the hole in what we call electron hole recombination. So when they recombine, and that's when the semiconductor is in steady state equilibrium, they will not cause sufficient increase in the number of electrons or hole. Then the mean time over which excess electrons and holes exist before they recombine is called excess carrier lifetime. So the excess carriers will become fundamental in solar cells and photodiodes, in the mechanisms of solar cells and photodiodes that we're going to be considering in section 1.5.